So as promised, we're going to use the big integral tables. I might as well put big integral tables to evaluate the following. Some of the integrals require preliminary work such as completing the square or changing variables before they can be found in the table. Yes, so that's a good thing to note. Sometimes you're going to have to do some preliminary work, right, using algebra and pre-calc and trigonometry, that kind of thing, in order to be able to use the big tables. And I might not always remind you of that fact. Oh, I guess I should say sometimes. You'll have to figure it out yourself. All right, so looking at this one actually doesn't require any early work. We can make this one work. So you kind of have to fly through and find what works for you. So just looking at it, we have x plus 1 inside that square root, right? So if we look at it this way, we have x plus 1 in there. So that's sort of an a plus bu, right? So a would be 1, because a's are constants. Remember the way these tables are set up. A, B, and C, and both types of C are always constants, right? X is your variable, right? And U is your variable. So if I look at this one, it's sort of written in A plus BU. So actually it definitely is. So let me rewrite that. If it's the square root of x plus 1 is the square root of 1x plus 1, this is A, and that's u. So u of x, which is u, is 1x, and then this is a constant. So I would say that a is 1, b is 1, and I have an a plus bu. Okay, let me rewrite it. Or bu plus a form. So then I notice in my lovely table, after hunting, I notice that I have this square root of a plus bu form. Huh, that's handy. Hey, look at number 19. It's got a u out there, right? U is x. So u of x was 1x. So let me change that just a little bit, because if I'm going to do it in that form, if I'm going to say a plus bu, then I'm going to say a is, here I'm going to say b is 1, a is 1, and x is going to be my u, like that, right? So bu plus a, that works better. All right, so then, I mean, we could, well, it would work the other way too, but it'll work out nicely this way. All right, so that means that I can use number 19. So if I know that b is 1, u is x, and a is 1, and of course, if u is x, then du is dx, right? So that works out beautifully, right? That means that I can just use the formula. So I can say, all right, this is equal to my original integral is equal to 1 over, oh, I have to check. Is a greater than 0 or is a less than 0? All right, a. A for me is 1. That's my constant term, which is greater than 0. So I'm going to use the top portion. Oh, sorry. I apologize. There we go. All right, so I'm going to use the top one right here, right? So I'm using number 19. So I'm going to write that. Number 19. Technically, I'm using the top one, right, of number 19, but that's unusual to have two of them. It's not unheard of. It happens a couple times in the table, but all right, so I will say it's 1 over the square root of a, natural log, absolute value, a plus bu minus the square root of a plus bu plus the square root of a plus c. All right, so there's the formula. So now I'm going to substitute in a, b, and c. Well, c is a constant, so a and b. 1 over the square root of 1, natural log, absolute value, minus the square root plus the square root, right? So this will be a plus, this will be a plus. So it'll be 1 plus bu, so 1 plus 1x, minus the square root of 1, 1 plus 1x plus the square root of 1, plus c, because c is just that constant of integration. Okay, now just cleaning that up just a little bit, because that's just the formula. So that's the square root of x plus 1, or 1 plus x, you know, either way. Doesn't make any difference, right? Addition is commutative, so minus 1, because the square root of 1 is 1. Square root of x plus 1 plus 1 plus c. Just for fun, let's check this on something like Wolfram alpha. It's always fun to check. All right, so I'm going to type integrate, let's see, 1 divided by, parentheses, x times the square root of x plus 1. I'm just going to press enter and see what happens. If I didn't do it right, it sometimes does a good job. Oh, see, it made an attempt to fix my missing parentheses, which I knew I did. And now it looks like that. But that's the same thing. First of all, LOG, because this is British, LOG is LN. They're actually the same thing. And second of all, they've got it kind of backwards from us, but it'll work. Let me write that down real quick. So CAS check. It says LOG of 1 minus the square root of x plus 1 minus LOG of square root of x plus 1 plus a constant. Like that. And you can see, remember that logarithms, of course, with subtraction are actually division. So it's really this divided by that. And the reason this is reversed is because we have absolute values and they don't. So in order to make this turn positive, they've reversed the sign, right? That what would happen. That is what would happen if we used our absolute values to their full effect, which we didn't bother. So this actually is the same answer. It just doesn't look like it. And again, remember that in foreign countries, which Wolfram Alpha is developed by originally people in Britain, now, of course, by people all over the world, but LOG in many countries is LN. LN is actually a very American thing. It's taking place, or it's starting to take hold around the world in lots of different contexts, but nevertheless, it's not universal. So that's an interesting comment about LN versus LG, or LOG, I should say. All right, now what about letter B? Well, in letter B, I kind of notice to myself, well, I noticed that I should have given it more room. Sorry about that. But I noticed that if I make u e to the x, right, because I can, then du would be e to the x, dx. No problem. So then let me rewrite this with, I think, a different color. Here, let me go blue. Okay, so then this integral, I have to go down, sorry about that, is equal to the integral of 1 over u, or square root, sorry, 1 over the square root of u squared plus 4. And then all that e to the x dx business becomes our du. And at that point, we want to go look for a form that would fit that amongst the 121 different tables that we have. We have a whole bunch of them. All right, and you can see there's actually two options for this one. You've actually seen this one before. Square root of u squared plus a squared, right? A squared is 4. So a is 2. So this is really u squared plus a squared. There are actually two versions. They're alternate versions of the same thing. So we could do this bit right here with the logarithm, or we have an alternative. If u is greater than a, we would use arc-cosh, and if u is if u is less than a, it should be. Oh, it's because this one's plus and this one's minus. That's why. So if u is greater than a, you can use this one if it's plus or this one if it's minus. And you'll notice this one actually has a plus or minus inside of it. So we could use either one of those. There's logarithmic form and there's hyperbolic form for those ones. So we would just tell ourselves, hey, we're going to use formula number 34, which would be the natural log of the absolute value of u plus square root. And then with these ones, you follow the form. So because we had a plus, which is the top one, you'll stick with the plus, which is the top one right there. As opposed to look at number 36. See the plus right there, but then it goes with the minus right there, right? You go plus goes to plus, minus plus. Minus there would go to minus plus minus, right? So you follow the order. All right, so but this particular one, plus goes with plus. So I'll write u squared plus a squared, which was 4, plus c. So that would be the natural log of the absolute value of u, which was e to the x, plus square root e to the 2x, right, u squared, plus 4. Alternatively, we could have used the 34 alternate. So we could also say, or number 34 alternate, and it would be u over, arc cinch of u over a plus c, which would be the arc cinch of e to the x over 2 plus c. Right there. So this one would also work. And what's amazing is that those two are actually the same thing. It has to do with, remember, the cinch formulas and the arc cinch formulas and so on. But they are actually the same answer. Notice that you always clearly denote somewhere which formula you're going to use. And sometimes you may need to use more than one. It doesn't happen very often. But this particular one, I had to do a little bit of setup work just to see which formula I needed to use. That happens. And if we want to check ourselves, let's see, I could check myself in Maple. Why not? All right, so if I'm going to check myself in Maple, it would be the, oh, you know what? You guys don't have access to Maple, so let me use Wolfram Alpha instead, just to give you guys something. All right, so I'm going to integrate e to the x divided by square root of e to the 2x plus 4. And you'll notice when it comes up, it should look like, see, it didn't. See, it's not the right one. And you can see there's an error function. That's the error function. All right, so I have to put an extra parentheses in here. E to the 2x plus 4. There, and I'll redo it because I could tell that it wasn't the correct integral. There it goes, arc cinch of e to the x over 2. And then there's the alternate form right there. See? The logarithmic form looks a little bit different, but they're just playing around with the plus 4 that we had in there. They're factoring out a 4 and kind of messing around with that. So don't stress about that too much. You can still tell it's definitely in the same vein as our work, and that's fine.